Hello everyone, welcome to Learn Wireless Technology. In this tutorial, we will discuss the protocol stack of LTE network. We will talk about the user plane and control plane protocol stack architecture and different layers in the protocol stack. We will also see how does a data packet flow across different layers when data is transmitted from either UV to network or network to UV. So let's start. The protocols over the air interface, that is between UV and EUTRAN, and over S1 interface, that is between EUTRAN and EPC, are divided into two structures. They are user plane and control plane. Let's have an overview of both these structures. The user plane protocol stack is responsible for transferring user application data. The EPS pairer established between UV and PDN gateway carry the user data through the access stratum. The user plane protocol provides the ERAP services that helps in transferring user data. The control plane protocol stack is responsible for transferring signaling messages. These protocols control the ERABs. It manages and controls the signaling aspects between the UV and network, such as requesting for a service, controlling different transmission resources, mobility, and security. Both the protocols provide a mechanism for transparent transfer of NAS messages between UV and MME via eNodeB. We will quickly see the concept of SDU and PDU. We will be coming across these terms lot of times ahead, hence it is necessary to understand this now. SDU is Service Data Unit and PDU is Protocol Data Unit. The data packet received by any layer is called an SDU, and this SDU is modified by that layer and transmitted as PDU. The modifications done by a protocol layer can be encapsulation, concatenation, segmentation, padding, etc. Let's understand this with the help of a diagram. Consider these different protocol layers at the sending side. Let's say for example, this is the protocol stack of a UV, and this is the protocol stack layer of the receiving side, that is the eNodeB. Now the data packet that enters any particular layer is known as SDU. Let's consider layer n plus 1 which receives a data packet or an SDU from its upper layer. Layer n plus 1 will modify this SDU by adding a header or segmenting or concatenating the packets or add some padding to it. The new packet formed after these modifications will be transferred to the next layer below, that is layer n. So a packet entering layer n plus 1 is referred as layer n plus 1 SDU, and after modifications when this SDU leaves the layer n plus 1, it is referred as layer n plus 1 PDU. Now when this layer n plus 1 PDU enters the next layer, that is layer n, it will be referred as layer n SDU. And when this SDU leaves the layer n after modification, it will be referred as layer n PDU. This concept is followed across all the layers, even at the receiving side. The direction of the packet flow is shown by the arrows as you can see. So this was all about SDU and PDU. Let's take a look at the user plane protocol stack architecture. This is the protocol stack at the UV end, and this is the protocol stack at eNodeB, that is EUTRAN. At lower layer, we have physical layer, which is the layer 1. MAC, RLC and PDCP constitutes the layer 2. And above that, we have the application layer, which represents the highest layer, and it receives data transfer services from lower layers. The physical MAC, RLC and PDCP layers at UV terminates at their respective counterparts at eNodeB. It means that a layer or entity at UV side communicates with its peer layer or entity at eNodeB side. LTE is the interface between UV and eNodeB, which is nothing but the air interface. This is the protocol stack layer at eNodeB that terminates at serving gateway. The connection between eNodeB and serving gateway is based upon S1 user plane protocol. The lower layer L1 is the physical layer which is based on electrical or optical connection for transferring data to serving gateway. The GTPU layer at the top represents the GTPU tunnel that is used to transfer user data between tunnel endpoints. The GTPU packets are transferred using UDP protocol over IP. Similar connection is present between serving gateway and PDN gateway. GTPU tunnel is established between these two nodes and they represent a pair of endpoints as well. The connection between serving gateway and PDN gateway is based upon S5 S8 user plane protocol. The IP layer of UV terminates at IP layer of PDN gateway. PDN gateway assigns IP address to UV, which is used to transfer user data over the packet switch network. PDN gateway connects to the external application server via SGI interface. The application layer at UV terminates at application server. PDN gateway routes the IP packets towards the application server. So this is the complete protocol stack of user plane. As you can see, the eNodeB, serving gateway and PDN gateway relay the application data between UV and application server. Now let's go through the user plane protocol in little more detail. We will focus mostly on the protocol stack layers over the air interface, that is between UV and eNodeB. We saw in the architecture before that the sub-layers MAC, RLC and PDCP at UV side terminates at eNodeB on network side. We will see the list of functions supported by each of these layers. We will concentrate mostly on the air interface protocol stack between UV and eNodeB. Let's start with the functions of MAC layer. The mapping between logical and transport channels happens at MAC layer. The logical channels carry the RLC PDUs which are mapped to the transport blocks to be sent over the transport channels. We will discuss in more detail about the channels in LTE in coming tutorials. The multiplexing and demultiplexing of MAC SDUs takes place at this layer. MAC SDUs are nothing but RLC PDUs, which is the output of RLC layer. MAC layer performs the scheduling related functions in uplink and downlink direction. Now the scheduling is done at eNodeB, hence MAC layer is responsible for reporting scheduling related information such as UV buffer occupancy and power headroom. MAC layer also supports HARC to improve the reliability of transmission. Error correction allows MAC layer to inform RLC about any transmission failure so that the packet can be retransmitted. In case of dynamic scheduling, the MAC layer handles the priority between the UVs. Dynamic scheduling is used to allocate resources for retransmission, so it decides which UVs should be given priority for retransmitting packets. Now let's look at the RLC layer functions. RLC layer performs concatenation, segmentation, and reassembly of RLC SDUs. The RLC PDUs are resegmented and reordered before transferring to MAC layer. RLC layer also detects any duplicate packets and if there's any protocol error in any of the packets. Now coming to the PDCP layer functions. PDCP layer performs header compression and decompression. Header compression is based on a method called ROHC, that is robust header compression. It is used to compress the size of the header, which reduces the signaling overhead in the data packet. It also improves the overall bandwidth efficiency. The ciphering and deciphering of user data is also done at the PDCP layer. GTPU protocol, as we discussed before, it establishes a tunnel between two nodes for transferring user data. It is used over S1 interface between eNodeB and serving gateway. GTP tunnel is also used over X2 interface between two eNodeBs. It is applicable during inter-eNodeB handover. The overall EPS bearer for transferring user data is formed using radio bearer, which is between UV and eNodeB, S1 bearer, which is between eNodeB and serving gateway, and S5 bearer, which is between serving gateway and PDN gateway. Uplink and downlink data traffic are mapped onto proper bearers or tunnel IDs based on traffic flow template. Traffic flow template are a set of packet filters for the UV that is applied in uplink and downlink direction. Moving on next, let's now discuss the control plane protocol stack. The control plane protocol stack is responsible for control plane signaling. The RRC and NAS layer at the top of the protocol stack at UV end are used for RRC and NAS signaling purpose. The rest of the protocols at the lower layer is same as that of a user plane. These are the protocol stack layers at eNodeB side. The protocol termination of the lower layers, that is MAC, RLC and PDCP between the two entities, are same as that of user plane. And LTE-UU is the physical layer interface between them. Now the layer 2 protocols, that is PDCP, RLC and MAC layer, deals with the signaling messages that are transmitted through control channels. PDCP handles the integrity protection and ciphering of control messages. RLC layer is used to transfer control plane signaling messages in transparent or acknowledged mode. MAC layer is responsible for prioritizing and multiplexing of control and user data from logical channels. It also supports link adaptation and HARC. The RRC layer is used for signaling between UE and eNodeB. It uses signaling radio bearers or SRB for transferring signaling messages. The examples of RRC messages include RRC connection request, RRC reconfiguration request, RRC connection release, paging, etc. As you can see here, there is no NAS layer present in eNodeB. Hence, the NAS layer of UE communicates directly with the NAS layer of MME. This is the protocol stack layer between eNodeB and MME, and the protocol layers terminating at their corresponding peer entities. And S1 MME is the interface between them. So here eNodeB is responsible for transferring the NAS messages between UE and MME, as eNodeB is the radio interface termination point of UE. The NAS messages are piggybacked into the RRC messages while transferring between UE and MME. eNodeB only reads and interprets the RRC messages that is meant for it. It does not interpret the content of NAS messages and forwards straight away to MME or UE as received. The physical layer processes the data from transport channels by modulating and coding the information. The data is mapped to the resource blocks and OFDM signal is generated to be transmitted over the air interface. Now let's look at the lower protocol layers between eNodeB and MME. The S1AP protocol at the top is used for signaling procedures and transferring messages between eNodeB and MME. The S1AP protocol deals with end-user connection procedures such as ERAP setup, modification and release, handover preparation, resource allocation, transport of NAS messages, etc. It also deals with network management functions such as S1 setup, eNodeB and MME configuration update, eNodeB and MME status transfer, etc. SCTP, that is Session Control Transmission Protocol. It provides a reliable data transfer service. It is an alternative to TCP and UDP. SCTP supports retransmission, which makes it more reliable. It allows transmission of signaling in parallel streams. The IP protocol is used to route the IP data between eNodeB and MME. The physical layer connection between eNodeB and MME are based upon electrical or optical connection. The interface between them is S1 MME or S1C interface. Now, similar to this, we have X2 control plane protocol stack, which is used for signaling between two eNodeBs. The interface between two eNodeBs is X2. The X2 application protocol or X2AP at the top of the protocol stack supports various procedures related to mobility. The messages transferred between them are known as X2AP messages. The X2AP messages include handover request, handover acknowledgement, releasing UV context, setup and release of X2 connection, etc. These messages are primarily used during inter-eNodeB handover. The rest of the layers below the X2AP layer is same as those below S1AP layer in S1 control plane protocol stack. SCTP is used over IP for transferring signaling messages, and the physical layer is based upon electrical or optical connection. Let's discuss a little more on control plane protocols. So the PDCP, RLC and MAC layers function the same way as we saw for the user plane. RRC layer is responsible to perform some important functions. RRC messages are exchanged between eNodeB and UE for various purposes. eNodeB broadcasts master information block or system information messages to UE. These messages contain useful information that help UV to establish a connection with the network. eNode B also sends paging messages to UV. Paging messages allows UV to know if there is any downlink data available to be received. RRC layer manages the RRC connection between UV and network. It allows UV to establish an RRC connection during initial attach process or when UV wants to move to active state from idle state. It releases the RRC connection when UV moves to RRC idle state. Any modifications to be done on existing RRC connection is done using RRC connection reconfiguration message. When UV loses an RRC connection, then the connection is set up again using RRC connection re-establishment. RRC layer supports in mobility functions such as handover, cell reselection, cell redirection, etc. UV reports measurement data such as RSRP, RSRQ, SINR, RSSI of its serving and neighbor cells. Based on the measurement report, the UV's connection with the network is controlled. During mobility, UV will be moved to a different cell or eNode B based on the measurement it reports using RRC procedures. The NAS layer is responsible for handling functions such as managing the EPS bearer. EPS bearer establishment is part of attach procedure or PDN connectivity procedure. Once bearer is set up, then based on different conditions, the bearer can be modified. In scenarios such as handover, which requires change in serving gateway, and also when QoS parameters needs to be modified as per service request, then EPS bearer modification is required. And when user ends the active session, EPS bearer shall be released. Mutual authentication and establishing security context at NAS and access datum level for secure transmission of data is also a functionality of NAS layer. NAS layer also handles the mobility of UVs in ECM idle state. S1AP and X2AP, as we discussed, are the two radio network layer application protocol. S1AP supports signaling procedures such as radio access bearer management, paging, NAS transport, etc. And X2AP supports inter-eNode B handover mobility, load management, X2 error handling, etc. Both S1AP and X2AP uses SCTP for transmission of signaling due to its high reliability, better redundancy, and better transmission efficiency. Now let's see the overall picture of how the user data or a signaling message is transferred from higher layer to lower layer. We will see this only for the radio interface protocol between UV and eNode B. Let's first start with layer 3. These are the protocol layers of layer 3. NAS and RRC are the protocol layers of control plane, and Internet protocol is the layer of user plane. There is also an application protocol above the Internet protocol, but it is not shown here for simplicity. Layer 2 protocols. It consists of PDCP, RLC, and MAC layer. They are used to transfer both signaling as well as user plane data. Finally, we have layer 1, which is the physical layer. The data reaches the physical layer to be transmitted over the air interface. Basically, the lower layers in the protocol stack provides data transfer services to the higher layers. The data that originates from higher layer needs to be transmitted through a medium for which the lower layers support them by applying different procedures to the data to make it suitable for transmission and providing channels so that the data can be transmitted. We have already discussed the functionality of each layer previously. The user data from IP layer is transferred to PDCP layer. PDCP will perform header compression and ciphering of user data. PDCP layer transfers this data known as PDCP PDU to RLC layer. Between PDCP and RLC layer, there are radio bearers present that carries the data. Radio bearers can be signaling bearer or data bearer. RLC layer will perform segmentation, concatenation, and reassembly of the data. It will transfer the packet in either of the three modes, that is, transparent, unacknowledged, and acknowledged mode. RLC layer maps this data known as RLC PDUs to different logical channels and transfers them to MAC layer. MAC layer will multiplex or demultiplex the data, add padding bits to it, and forms a transport block. This block is mapped to different transport channels and sent to physical layer. Physical layer will process the data packet. It will perform scrambling, modulation and coding, map the data bits to OFDM symbols, generate OFDMA signal, and transmit over the air interface. Now let's look at the control plane part. The signaling message from the NAS layer reaches the RRC layer. RRC encapsulates the NAS message inside RRC message and transfers it to the PDCP layer as RRC PDU. Here you can see the RRC layer controls the data at each layer by providing control information on how the data must be treated at each layer. Each layer will then perform different functions and process the data as instructed. So this complete procedure that I just explained applies to the sending entity at either UV side or network side while transmitting uplink data or downlink data. Now the same rule applies for the receiving entity as well, but in exactly reverse way. So let's summarize the concept quickly. The radio air interface protocols between UV and eNode B in access stratum consists of three layers. Layer 1, that is physical layer. Layer 2, that is MAC, RLC and PDCP layer. And layer 3, that is RRC layer. The data flows from higher layer to lower physical layer at the transmitter end and from physical layer to higher layers at the receiver end. The lower layers serve the higher layers with data transfer services. Some of the services provided by the lower layers to the application data from the upper layer are ciphering, segmentation and concatenation, multiplexing, mapping of data to channels, resource assignment, etc. So with this we come to the end of this tutorial. I hope you understood the LTE protocol stack layer, control and user plane protocols, and how the data is transmitted from one entity to other. Thanks for watching.